Good morning, one and all. My name is V. Abhijit Kumar. I am studying in Computer Science and Engineering, Artificial Intelligence and Machine Learning. That is CSC, AI and ML, BTech first year, first semester, Institute of Aeronautical Engineering. In this tech talk of the subject of matrices and calculus, I am going to discuss about the topic of the generalized inverse inequalities for symmetric non-negative definite matrices. First of all, I'm going to introduce the topic and I'm going to explain the definitions and the notations related to it, and I'm going to explain about the key inequalities, and after that properties of generalized inverses, which we are going to discuss, and after that I'm going to discuss about the applications of those inequalities, and after that I'm going to explain about the challenges which we may have to face and open questions which can rise in anyone's mind, and finally after all these I'm going to conclude the topic. Introduction. Symmetric non-negative definite matrices. Such kind of matrices are simply known as square matrices, which have non-negative eigenvalues. Such kind of square matrices are quite common in the chapters like linear algebra, statistics, optimization, and many more. Generalized inverse. The concept of generalized inverse of such kind of symmetric non-negative definite matrices extend the concept of inverse to singular or non-square matrices. For example, Moore-Penrose pseudo-universe. Importance of such kind of inequalities. Key to stability analysis and bounds in numerical methods, which means that only such kind of inequalities can key to stability analysis and bounds in numerical methods and many more. Now let's talk about definitions and notation of such kind of matrices. Symmetric matrix, we know, is any kind of matrix which is equal to its own transpose. That is, A is equal to A transpose. For non-negative definite matrix, X transpose into A into X is greater than or equal to 0 for all values of X which belong to rational numbers. Generalized inverse is such kind of matrix A that satisfies A into A transpose into A is equal to A. Notation of such kind of matrices is the determinant of A is matrix norm and the eigenvalue of A is notated by lambda into A. These are the definitions and notation of non-negative definite matrices. Now let's talk about key inequalities of such kind of matrices. For symmetric non-negative definite matrices A and B, which means if we consider any two matrices out of which one is defined as A and the other one is defined as B, and if those two matrices are symmetric and non-negative and definite, the trace inequality is that the rank of the sum of those two matrices is greater than or equal to the traces sum of those two. That means R of A plus B is greater than or equal to trace of A plus trace of B. And the determinant inequality is that the determinant of sum of those two matrices is equal to or is greater than the sum of determinants of those two matrices. That means determinant of A plus B is greater than or equal to determinant of A plus determinant of B. And last, eigenvalue inequality is that the eigenvalue of the sum of those two matrices is greater than or equal to the eigenvalue sum of those two matrices. That means eigenvalue of A plus B is greater than or equal to eigenvalue of A plus eigenvalue of B. These three are the key inequalities in the scenarios of such kind of matrices. Now let's talk about properties of generalized inverses of such kind of matrices. Existence. A plus exists for all matrices A, which are not necessarily invertible. The next property is uniqueness. Moore-Penrose pseudo-universe is unique. It's completely unique. The next property is commutativity. If A and B commute, so do their generalized inverses, which means that if we take those two matrices A and B, and if we can be able to commute each other, then we can commute their generalized inverses too. And the fourth property is that the property of non-negativity. If A is non-negative definite, A plus is also a non-negative definite. These are the properties of generalized inverses. Now let's talk about applications of such kind of inequalities. The first application is optimization. In other words, it is the process of constraining solutions in convex problems. The second application is the application of signal processing, or in other terminology, it is simply known as the process of designing filters using eigenvalue bounds. The third application is the application of machine learning, or in other terminology, it is known as the process of regularization techniques in least squares. And the fourth application is the application of control theory, which in other terminology is known as the stability analysis of dynamic systems. So these four are the applications of such kind of inequalities. Now let's talk about the challenges which we may have to face and the open questions which may rise in such kind of scenarios. The first challenge is the challenge of computational complexity. In this challenge, the open question may rise about the efficient computation of A plus for large matrices. The second challenge is the challenge of extension. In this challenge, the question may rise about inequalities for indefinite and non-symmetric matrices. The third challenge is the challenge of stability, in which the question may rise of sensitivity of generalized matrices to perturbations. And the fourth challenge is the challenge of numerical approximations, in which the question may rise about developing fast and accurate algorithms. These are the questions which are being raised by today's intellectuals. So these are the challenges and open questions. Now let's finally conclude this topic with two key insights, out of which one is that the generalized inverse inequalities provide bounds for matrix operations, which can be useful in diverse fields like optimizations, control, data analysis, and many more. And the future directions or the future scope for such kind of topics in such kind of scenarios is that it can be able to explore computational techniques for large-scale problems which can extend the results to broader classes of matrices. So finally, this is the conclusion of the topic. And finally, to the lecturer or to the professors who have assigned this wonderful topic to me, thank you.